Ahia Himarie. Good evening, everyone, and welcome to today's webinar brought to you by Rinnai, New Zealand. I'm Alice, your host and moderator. Thank you for taking the time to join us this evening as we talk about ring main systems. Now, while we're waiting for everyone to arrive, let's test our chat function by typing our answers to this question. What colours do Rinnai Infinity A26 come in? Please type your answers in the chat. What colours do Rinnai Infinity A26 come in? Type your answers in the chat. Black. Jacob, that's a good answer. Any other colours? Anyone? Ooh, Michael's got the term graphite. That's good to see. Several colours. Graphite and white. White graphite. Right. Lots of answers coming in. White and graphite. And the answer is indeed white and graphite. So the Infinity Graphite range also comes in A16 and EF26, our high efficiency condensing model. These models also meet light reflectance value guidelines. And remember to add those pipe covers, everyone, for a professional finish, unless if you want to show, the shiny pipes. Thank you all for sharing your answers, and good to know that chat is working. Let's make a start. So for those of you that just joined us, I'm Alice Wu, National Specification Manager from Rinnai, your host and moderator. Thank you for taking the time today to join us as we talk about ring main systems. Today's format will be 40 minutes of presentation, followed by Q&A. For a smooth running of the presentation, we kindly ask you to submit your questions in the Q&A section, and we'll answer them during Q&A time. Now let's start with a 30 seconds introduction about Rinnai. We're celebrating our 50th anniversary in New Zealand this year. Rinnai's mission is creating a sustainable, healthy and comfortable way of living. We provide a range of products and services that covers climate control and water heating solutions. For water heating, Rinnai has hot water heat pump, gas infinities, hot water cylinders and commercial solutions. For climate control, we have gas fireplaces, gas central heating, electric fireplaces, Warmington wood fires and heat pumps. Without further ado, it is my pleasure to introduce our speaker for today, Grant Burke. And Grant has been in the hot water game for over 40 years. As Rinnai's commercial hot water manager, he's the go-to guy for everything from system design and installation advice to troubleshooting the trickiest faults across both residential and commercial projects. With a mechanical engineering degree from the University of Auckland, Grant has dedicated his career to advancing water heating technologies and sharing his knowledge with the industry. His background includes lecturing in the building services at AUT, and he continues to be a respected educator through Rinnai's webinar series. What sets Grant apart is his ability to make complex technical stuff easy to understand. Whether you're a gas fitter, plumber, engineer or specifier, his sessions are packed with practical tips you can take straight to the job site. When he's not talking about hot water, you'll likely find Grant out cycling, playing a round of golf, or enjoying time on the water. Over to you, Grant.
Thank you, Alice, for that introduction. I seem to get cleverer as AI gets better at writing bios. So thanks, everyone, for taking your time to come this evening. We are about to release a booklet on ring main water heating systems. It should be out towards the end of next week. This webinar is going to cover most of the topics, many of the topics, but a very once-over lightly format as to what's in the book. So once the book's available, we encourage you to get your hands on one, and it goes into much more detail than we can cover off in 1 hour tonight. We've done this because we get so many questions about ring main systems, so we decided it was time to put all the information that we had in various parts into one place and make it available to plumbers and engineers that are starting on their journey of creating ring main water heating systems. So what we're going to have a look at tonight, basically what's a ring main, the benefit and limitations, some building code compliance, hot water ring mains, warm water ring mains, which of those I should be looking to use, how to size the pipe, how to size the pump, a bit about UV sterilizers and warm water systems, expansion chambers, how to minimize the running costs, and then we're going to have a quick look at the different water heating technologies because each needs a slightly different approach to the installation of the hot water plant when we are building a ring main system. And really the scope we're going to look at tonight is sort of larger houses and small commercial buildings. We're not going to cover large multi-story buildings. The same principles apply, but it's a little more complex, and there's a few things that we're not going to cover off tonight that you need to know if you want to have a crack at a larger building. So sort of seek a bit more advice if you're doing a larger property. So just to make sure we're all on the same page, because we'll all be at different levels, we've got a reasonably large single level house here. We've got the water heater sitting in a cupboard in the hallway. And so if I turn the water tap on, hot water on to wash my hands after I've been to the toilet in the middle of the night, I get a bit of hot water down to my ensuite. It takes a little less time to get the water to my shower because I've already warmed the pipe up a bit. If I'm way down the other end of the house in the master ensuite, I'm waiting a fair while to have the water arrive. If I'm in the kitchen, I'm also potentially waiting a fair while to have the water arrive. Now, in terms of compliance, this distance from the water heater to the kitchen sink is regulated under Building Code Clause H1, eventually calls up Standard 4305, which sets out a little table of lengths. These lengths, typically for high-end houses, if you work out to the maximum of these lengths, the customer's pretty unhappy because the water can take 45 seconds to arrive at the sink. So for a large house, the customers are often looking to do better and they want to turn the tap on and have the hot water arrive straight away. So what we do is we add a small diameter pipe from the furthest fixture. We can now put the water heater plant anywhere we like, and we run a circulating pump which constantly pumps hot water around the ring main of the house and then back to the hot water plant. So now when I turn a fixture on at my kitchen sink, the water arrives near instantly, and other fixtures the same. Importantly now, my distance called up under H1 of my pipe run is very short because it's only the distance from the ring main to the fixture. So let's have a look at what's good about a ring main and what's not so good. And throughout this next half an hour, we're going to have a look at how we can mitigate some of the things that are not so good. So what's good about them? We turn the tap on, hot water arrives straight away. It's the biggest single query we get from customers about water heaters when we're standing at home shows or other places we were interacting with consumers. My hot water takes too long to arrive at my tap. We can now put the water heater anywhere. It can be outside, it can be in the far corner of the garage, it can be in the attic, it can be anywhere we like. We're not looking for valuable real estate in the middle of a house to locate the water heater. We're going to reduce the water use because we're not going to turn the tap on at our shower, admire ourselves in the mirror for 10 minutes while we wait for the water to arrive and be nice and warm. So some of the limitations, they can be more expensive to install. There's obviously more stuff, requires a lot more planning, and we'll go into some of that as we go through. Plumbers may lack familiarity, and that exhibits itself in two ways. One is plumbers are reluctant to take it on, and the second is because they don't know how to cost the job, they're not quite sure what's involved. They may overquote because they don't exactly understand what's involved, and I guess that's what we're all here for today, is to understand a bit more about these systems. Another limitation is that if you've got hot water running around a pipe in your house constantly, that will be losing heat at a constant rate. So you're up for a fixed running cost from the heat loss. So we want to look in today about how we can minimize that fixed running cost from the heat loss. This came up very obviously from hotels during COVID. They were ringing us saying, why is our gas bill so high? Nobody's here using hot water. And what they were seeing for the first time was the first evidence of the fixed running costs from the ring main. Nobody's staying, but keeping that ring main hot was costing them a lot of money. Particularly important for LPG as it's more expensive than other energy sources. So building code compliance, if we look at clause G12, so we've got a couple of performance requirements. We've got 3.6, so it can't be too hot. So how we go about that is obviously our sanitary fixtures for personal hygiene, depending on when the fixture was installed or whether you're at a installation with vulnerable people, we need to limit the water temperature, and we do that using mixing valves at the branch offtakes or for the whole ring main in order to reduce the water temperature. The second clause is preventing Legionella. So we, as always, store water at 60 degrees. Any water going around the ring main at less than 60 degrees, we need to clean that up via a UV sterilizer before we send it around the ring main again. So a big one here, building code compliance, all components must be suitable for potable water. So when we're into ring mains, we're into some components that have got a lot of similarity with hydronic heating. And the hydronic heating components aren't certified for potable water. Often suppliers have similar looking components for hydronic heating and for potable water that aren't certified for both applications. And the hydronic heating ones are normally cheaper. They're not lead-free brass and so on. So a common one that I see, if you look at these little Grundfos circulators from left to right, the one on the left is stainless steel, the one in the middle is bronze, and the one on the right is cast iron. I walk up to an awful lot of ring main installations and I see a little black escutcheon on the Grundfos pump indicating it's cast iron, and it really shouldn't be there. So just a word about that. Other Grundfos circulators that are bronze have black escutcheons on them, so it doesn't mean that all black markings are bad, but you need to make sure that you're using the right components for potable water. And again, the ones for heating are generally cheaper, so make sure that you're onto your merchant and make sure that the one he's quoted you and the one you're getting is not the cast iron one, that it's actually for potable water. Another one here, the leafy expansion control valve, blue one, potable water, red one for heating system. I mean, you might think red one's for hot water, but that's the one for the heating system. So we need to be avoiding that one. It's not certified for potable water. So we've got two fundamental types of ring main. We've got one for hot water. We'll see if my voice lasts this webinar. So we're going to circulate the water at greater than 60 degrees, send it off from the hot water plant at more than 60, often 65 degrees. We're going to use mixing valves at the branch offtakes or close to the fixtures to reduce the hot water at the sanitary fixtures to the applied or the acceptable temperature. We've also got warm water ring mains where we're still going to store any water at greater than 60. We're going to circulate the water in the whole ring main at a lower temperature, so we don't need to mix the water down at the branch offtakes. And any water that we recirculate, we're going to put through a UV sterilizer, and we'll have a look at that in a minute. So if we have a look at a hot water ring main, here's a schematic. This is in the book that'll come out, and you're welcome to contact us and we can send you CAD drawings of all these things. So let's work our way around this ring main. We're just showing a generic hot water plant. We're not worried about the hot water plant at this stage. We're just going to look at the ring main itself. So if we have a look as we come out of the ring main, we've got a couple of temperature measuring positions there. What can I say politely about this? It's really handy to have temperature measuring positions on ring mains. There's a compliance requirement about the ring main return temperature that it needs to be higher than 55 degrees. It's best done on small systems by installing Pete's plugs. You can then insert your temperature probe right into the middle of the flow. We go to lots of ring mains where we see T fittings and nipples and then a temperature gauge. And the temperature gauge is 100 millimeters or more from the actual water flow, and it doesn't give a reliable indication of what the temperature flow is. So for big systems, big pipes, 32 mils and up, you can put a dry pocket of thermal well in and put your gauge into that thermal well and make sure the thermal well is right in the water flow. For smaller systems, it's cheaper and easier to stick a couple of Pete's plugs in. If you haven't got the kit for measuring with those, you can buy it from your merchant, or they're available on Amazon, or you can get grandma to give you a set for Christmas. But it's really handy to have for both temperature and pressure. When you can get a little kit that's got 2 temperature gauges and 1 pressure gauge in it, super handy for this sort of work. If we then look at the offtake point mixing valve itself, there's a few things that we need to have in order to make this a good installation. So it must be located in an accessible position, and I'm going to explain more about that on the next slide, why that is. We need, so we can maintain in there, we want an isolating valve, we want a non-return, and we want some swivels either side. And I'll talk on the next slide about why that's so important. If we look down at the other end of the ring main here, and it might be the first, it might be the last, it can be anywhere, the offtake point to the kitchen. Obviously, we can go at higher than sanitary fixture temperature for that. However, what we suggest is having a chat with your client about what temperature they actually want to come from the kitchen sink, and you may want to put another mixing valve on those fixtures because the temperature of the hot water plant may be too high for what they want at the kitchen. If you've got a standard residential heat pump water heater, that's only ever going to be making just over 60 degrees, so you don't need it. If you've got a electric cylinder, you may leave it set at 60 and they don't need it. You need to have a bit of a chat with the customer that if they adjust their temperature up to 75 degrees in their electric tank, what's going to happen at their unmixed fixtures. So it's just a safety thing you need to be aware of. The H1 regulated distance for the kitchen fixture must comply to that 4305 table, to those lengths. However, if your customer's gone to the expense of putting a ring main in, they aren't going to be very happy if you've gone out to the maximum lengths from the ring main to the fixtures, because they'll still be waiting a long time for water. So you really want to keep those branch off takes as short as you can by routing your ring main as reasonably close as you can, particularly for basins. Typically the return pipe's going to be 1/2 inch or thereabouts, but we'll go into the sizing of that in a bit more detail in a few minutes. We also need a non-return on the ring main return. If we don't have this, when I turn a fixture on, I run the risk of cold water entering back up the ring main and out the fixture, and the pumps are only small and they are not going to overcome to any close degree the water pressure that you've got in the system. So we need a non-return to stop the cold incoming water taking a shortcut. The final thing we need is some pressure relief somewhere in the system. We're obviously going to heat up this pipe, and it's just like when you heat up the water heater, you need to have the pressure relieved somewhere. Most systems you can use the expansion control valve in order to relieve the pressure, but you just need to be a bit mindful of where you place it, and we'll look in the drawings about that as we go through. So that's the standard high temperature hot water ring main mixing valves at each offtake point. So if we just have a look at these valve sets, the non-returns, so I should have said you need a non-return in these systems either side of the mixing valve. You don't want to have one with a mixing valve one side only, you need both sides. Now this results in cross connections when the non-returns stick open over time. And I've spent many glorious hours crawling around buildings looking for the mixing valve that's causing the cross connection. So if we look at this pair of offtakes from the ring main here, we've got this non-return here. Let's say that is stuck open. I'm now going to turn a hot fixture on the other offtake point, and instantaneously, because I've got more flow from the hot water line than the cold water line, I'm going to have a lower pressure in the hot water ring main and in the cold water delivery line. So I'm going to have more pressure in the cold water side than I have in the hot water side. So this cold is going to sneakily jump across here and get into my domestic hot water line. This seems a bit sort of theoretical. I've been to buildings that are 20 years old with reasonable numbers of these fittings, and the cold water is actually lukewarm, and the hot water is also lukewarm, and the customer's pretty unhappy. So this does happen. So it's really important that we provide for access to these valve kits. I've also been to buildings where they've big buildings, like apartment buildings with 100 apartments, where they've put these in, they've put a beautiful access hatch, they're easy to get to behind the bathroom door, but they haven't put any isolation valves in. So the whole building's going to be shut for a couple of days while the plumber goes around and cleans out all the non-returns and gets these cross connections sorted out. Many suppliers will do a nice little compact valve kit. That's one from Waterware that's got isolation valves, non-returns, swivels, mixing valve, and they'll sell them to you in a nice little cabinet. So if you can't get the valves under the floor or somewhere in the attic, you need to be talking to your client about where you can locate these cabinets that's not going to upset them. You can put them in the ceiling above doors and toilets or bathrooms, in the backs of cabinets, in wardrobes on an adjacent room. You just need to talk to the customer and get a bit tricky about where you're going to install these valves. But you really want to put them somewhere that you can get at them, because at some point, some poor sod's going to be trying to find these things to clean out those non-returns and get them going again. If we look now at a warm water ring main, which is similar but different. So we start out with the mixing valve. So what this is, it's kind of like a domestic tempering valve, but not quite. It's going to mix hot with cold and keep the whole ring main down to a lower temperature. Now, it's important that you talk to your supplier and read their specifications to make sure that the mixing valve you've chosen is going to work in this application. Not every off-the-shelf tempering valve will work. So you must make sure you've got a tempering valve, that the installation instructions show it, tempering a whole, mixing water down to lower temperature in a whole ring main. We want to, once we've commissioned the system, we want to adjust the temperature on that ring main so that the hot water coming out of the nearest sanitary fixture is no more than the allowable temperature, depending on when the fixture was installed. So it's important that we can get reasonable access to those valves also. Now that we're down to 50 degrees on ring mains, we've got a little less margin to play with than we had in the middle of last year when we could be 55. So you might want to talk to your customer about whether a 50-degree water, and you might want to run some 50-degree water out of a tap so that they can have a look at it and see what that means to them, as to whether you want to put a little under sink cylinder in the kitchen or the scullery to boost that temperature from 50 degrees up to perhaps 60 degrees at the kitchen sinks, because 50 degrees might be a bit shy, particularly if it's a long run and you're losing 1 or 2 degrees. You might be down to 49, 48 degrees. So have a chat with your customer if it's a new fixtures, new building, about whether they want to invest in a small electric water heater, 30 litres or something, to boost that temperature up at the kitchen sink if they think the 50 degrees less a bit's not going to rinse the gravy off the plates when they're washing up. This bit's kind of important, and I'll explain on the next slide how this works, but this is a leg that bypasses the cylinder on the ring main return and joins in with the cold before the mixing valve. I've been to lots of particularly smaller domestic installations with plumbers that have had a bit of a crack at a ring main that this is entirely missing. If this is entirely missing, the system won't work properly, water won't circulate properly, and I'll explain on the next slide why that is. And yeah, you'll stuff the pump and you'll stuff the mixing valve over time. So it's really important that this ring main return splits into two, and one leg of it goes back to the cylinder and the other leg of it goes to the cold side of the mixing valve. There are Yergamat 4-port mixing valves that have a fourth threaded connection on them that you can join this leg into, but it does the same as what's been drawn here. We've also got a non-return here. Again, it's really important that the cold water connection to the mixing valve is what I call virgin hot water, and that I've seen installations where the cold water expansion valve is the other side of this connection, and there's lukewarm water going up this cold connection to the mixing valve, and that it doesn't tend to become dangerous, but it exhibits itself as temperature fluctuations at times in the ring main. And given that you've installed these perhaps in your most discerning customers' houses, having temperature fluctuations is not a wonderful thing. So let's have a look at that warm water system. In the middle of the night, in the middle of the day, nobody's home, and there's no draw on the system. So what we've got is a fixed volume of water chugging around the ring main. As it goes around the ring main, it's going to lose some heat. So you see I've changed the colours from orange to yellow to indicate that it's lost a bit of heat. Now, when it gets to this leg of the ring main, it's going to split, and it's going to depend on how much heat it's lost. If you had an ideal situation where it lost no heat, all the water would simply go up this bypass and carry around the ring main. But that never happens. So most of the water in a well-insulated system will go up the bypass and go around again, which is why we need to put it through the UV sterilizer to clean it up. A small amount of the water is going to go back to the cylinder. And that water and going back to the cylinder, the mixing valve allows some hot to come out. And it's the mixing valve that's controlling all this. So we've got a little bit of water going in the tank, a little bit of hot coming out. And the balance of the recirculated water joins up with the hot, which tops its temperature up, and we're back to the temperature we started from. Now, this is a concept that's a little bit hard to grasp. I know when I was a young engineer, I struggled to get my head around this a bit, but this is what allows the system to keep circulating when nobody's got a tap on, but keep circulating it at the temperature that we want it to circulate at, not circulate at some higher temperature. So it's really important that we have this bypass leg that goes back to the cold side of the mixing valve. You'll see also there the note that these UV sterilizers, we'll have a look at one in a slide a little bit further on. They've got a bulb the length of the unit, and that we leave space in order to get the lamp out of that UV sterilizer. I've seen some really creative arrangements of pipes in order to allow people to get those bulbs out. So just have a bit of a think when you're laying out your pipe work. Make sure you've got the UV sterilizer there and make sure you've left yourself space to get that lamp out of that unit. So now if we look at that same warm water system, and let's say we've now got a water drawer on it, someone's turned a tap on. So we have some cold going to enter, hot's going to come out. We're going to have cold come up, go into the cold side of the mixing valve and come out. Now, the ring main's still going on at the same time, but that would be a very complicated picture to understand. These two things happen in parallel quite happily. But again, this illustrates why we want to make sure we've got sort of that virgin cold water coming from upstream of the non-return valve, so that the mixing valve, when this happens, is getting a nice steady temperature cold water. It's not fluctuating as a little bit of hot mixes in with it. So that's when a tap opens, what happens on that warm water system. So I hope if you never quite understood this, or you're seeing it for the first time, I hope that explains it and you can understand it okay. So the question is, should I use the warm water one or should I use the hot water one? What are the pros and cons? So generally, the hot water system is better for small systems where you've got small numbers of offtake points and you're going to have small numbers of mixing valves. You can obviously use, if you've got bathrooms close together, back to back, you can use a single mixing valve to do all the fixtures in a couple of bathrooms if they're close by. So generally for small systems, we're going to be into the hot water system. When we get large, we tend to go for warm water systems. When I say large, I don't necessarily mean a large house. I mean an apartment building with 100 units in it that we're not really talking about today. However, I was presented with a set of plans for a house in Papatoa the other day with 14 bathrooms. And so it was going to be really difficult. They were really spaced out. There was one ensuite for each bathroom, no bathrooms back to back. So the warm water system was going to be cost effective for that one. Getting fully hot water to the furthest outlets, obviously a hot water system is better for that. The warm water system, we need to insulate really well to make sure that the person at the furthest fixture isn't getting water that's not of a temperature that they feel is usable. Very hot water to the kitchen sink, obviously the hot water system does that better. The warm water system, as we saw on the previous slide, we can add a boost to it by putting a small electric tank in, but it all adds cost. Lack of places to put accessible mixing valves. We've seen buildings where in high-end homes, where the customers specified standard of finish was such that they weren't going to accept any hatches anywhere, so that the warm water system was the best option for those homes. Cross connection between hot and cold, we've seen it in warm water systems that best. So again, that's why we use them in large buildings, because we might have 200 potential cross connection points. So the warm water system is going to give us much less grief for that. In the warm water system, we've got to change the bulb every year. So in a big building, that's not a big deal. But in a small building, you don't have to do that with a hot water system. So it might be more beneficial in a smaller building to have a hot water system. So there's the pros and cons. It'll vary from project to project, but they're the things that you might need to bear in mind when you're considering whether I want to use the hot water system or the warm water system. The hot water's simpler if you're doing a largish house and you're having a crack at it for the first time. Within those two main systems, and we're not going to cover them tonight, you can dream up many different combinations of those systems and many different things that you might do with it. We can have multiple loop ring main systems. If your hot water plant's in the middle of the house and you've got wings going either side, you can run a loop to either side. Obviously, large buildings in standard have multiple loop ring main systems. We can have a low temperature ring main, but if we can get our hot water plant close to the kitchen, we can maybe take a dead leg just straight from the hot water plant to the kitchen. Similar thing, we could run a high temperature loop to the kitchen and scullery and a low temperature loop around the sanitary fixtures for personal hygiene. We saw this one, we can have a low temperature and have a boost cylinder at some fixtures. We can have a high temperature ring main, and we might decide that our hot water plant is making water that's too hot for the pipes we've got. I won't mention everyone's favourite system, but we might put a mixing valve in to mix the whole ring main down to 60 or 65 degrees and then have further mixing valves at off-take points for personal hygiene. And obviously, where we've got vulnerable people, we might have a higher temperature ring main and we might mix at those branch off-takes down to 45 degrees for those vulnerable people. And there's more variations on this, but we're not going to cover all this off because we're not doing a university course. We're just having a bit of an AR after work. But there's other things you can do. If you're considering one of these, give us a hoy and we're really happy to talk to you about it. Pipe size. So sizing the pipe, you do it basically whatever your usual method is for sizing pipe. ASNZS 3500, Appendix D's got one method. Whatever method you usually use, probably not to hold your finger in the air, but whatever method you usually use, go with that. Then there's one additional step you need to do. In a ring main, we want to keep the pipe velocities down so we don't wear the ring main out over time. So we're limited in ASNZS 3500.4. Please pretend you can't see the copyright label lurking in the background of the snip. And so our flow lines, if we're in copper, we need to be down at 1.2 meters a second. In other materials, we can go up to 2 meters a second. And in the return line, we're down to 1 meter a second for all materials. So once we've done our pipe sizing, we just need to go through and check that we're not above these velocity limits, not volumetric limits, but velocity limits for the pipes. In the book, I've converted these velocity limits into litres a minute for common pipe sizes to make it a bit easier. So a couple of notes here. It doesn't include where flow occurs only in response to activation by a user. Now, that's not that common in New Zealand. In California, some of their new building codes require that the ring main will only run when someone walks into a bathroom, so they're putting motion sensors that will fire the pumps up. So you can have a crack at that if you're doing a big house with a building management system or a smart home. Put a motion sensor in the various rooms and it'll keep the ring main running when there are people there. So for the return pipe, we're obviously just working out what the pump's pumping the water around at. In the supply pipes, we're going to add the flow rate that the ring main pump is causing, plus the normal simultaneous demand in the supply pipes. So in summary, same as what you always do, but you need to just check your pipe velocity so you're not going to wear the copper out. Pipe layout, just some general rules of thumb that are pretty obvious that I've spoken about. Get it as close to fixtures as you reasonably can. Minimise the branch offtakes from the ring main. So particularly if you're using a PEX pipe system where the T's, pardon me, have significantly reduced bores through the T's, that each of those is going to have a reasonably high pressure loss. So you want to try and minimise the number of those that you put into the ring main if you are, because you'll end up with a much bigger ring main if you put too many of those restricting fittings into the ring main. Obviously, NZS 3501 copper, the T's are full bore. They still have a little flow restriction, but not huge. So just bear this in mind. Don't get too carried away if you've got lots of offtakes and you're using a PEX system that's got restricted T fittings. Non-return on the ring main we spoke about. Temperature gauges and Pete's plugs we spoke about. Some pressure relief we spoke about. Air release we didn't. Often in a small domestic system, you'll get away without automatic air release valves. It depends just how you're going to organise the piping. You may need some on a 2 or 3 story building, but have a bit of a think about how you're going to get the air out of the system. In the book, we've got a couple of little tips that can help you with that one. Don't always need it with a simple system on a single level, but you can get into trouble if the ring main pumps we use aren't terribly grunty. So just have a bit of a think about the air release. Right, let's have a look at this ring main pump. So we need the right size of pump. Bigger is not better, and you'll see why in a minute. So what we're going to go through is a worked example where we've got a modest sort of single level place, and we've ended up with about 10 metres of 25 mil, another 10, reducing to another 10 metres of 20 mil, and going down to some 15 mil plus the return, and it's all going to be in 3501 copper. Same principles apply as to what I'm going to show you if you're doing it in other materials. So the first step you want to do is go and find the pump that you think's about the right size, and make sure that you're looking at the correct units. The pumps are litres a second, litres a minute, cubic metres an hour, metres a head, kilopascals. So make sure that what you're looking at is the units that you think you're looking at. If you're not looking at the right units, it should become pretty obvious as you go through. So sizing this pump takes a couple of iterations. And so what we want to do is get that pump curve for the pump we think we might want to use and have a look at the midpoint of that curve. So I've got here a Grundfos Comfort 1514B. Now I should say that tonight and in the book, you've already seen components from some other manufacturers that aren't Rinnai. We have no commercial arrangements with them. We've sort of chosen, and for the book, fittings that we know and components that we know are readily available in New Zealand, and they're reasonably well supported. There's many other components from your favourite suppliers that'll work fine. Just make sure they're suitable for potable water and check their specifications. So we're not advocating for anything, but it's always easier to show an example with real components in it. And we have no commercial arrangement. We're not getting paid for promoting these various fittings. My Swiss bank account's not rising as we speak. So we've got the Grundfos Comfort. We've checked that our units are in kilopascals and our flow rates in litres a minute. And so we've picked the midpoint of the curve, and we've got roughly 4 litres a minute, and it's going to do about 10 kPa. So what we're going to do is we need to work out our pipe layout, what the pipe pressure loss is going to be at that midpoint of the curve. Now, hydraulic engineers, if you're going to get them to do this for you, they'll have software that'll take care of this. This is sort of the manual way to do it on your kitchen table, but it works just fine for simple jobs. So we're going to use the pipe supply specifications to determine what that pressure loss is at 4 litres a minute. Now, I'm sticking with 3501 in this presentation. So what we've done is we've taken the 3501 specification sheet and we've converted it into a spreadsheet. And if you use this pipe material, at the end, we'll give you a link to the spreadsheet that you can download and use for yourself. So what we've done at the top left here, we've put our flow rate in, we've put the length of pipe in that we're going to use, and then we've put in the number of fittings that we're going to put in each length of pipe, which will increase the effective length of pipe. So what we've done is we've put all that in, and it's popped out that we've got about just over a 6 kPa pressure loss around that ring main. Now, our pump at 4 litres a minute is going to run 10 kPa of head. So what it means is the pump's going to increase its flow rate until the pipe and pump pressure loss and flow rates are balanced. So that's our first iteration. We weren't far off, but we need to increase that flow rate a little bit so we get those flow rates of pump and pipe balanced. So I had another couple of cracks at it, and what I found was that at 5 litres a minute, the pressure loss through my pipes is going to be 9.5 kPa, and lo and behold, at 5 litres a minute, my pump will do about 5.5 kPa. So what that means is if I put that pump in, note here also that I've allowed for a couple of valves either side of the pump and a non-return. Just a word about the non-return. These pumps are pretty small. If you use spring type non-returns with big buffy springs in them, the pump may struggle to get an initial open of that spring type non-return. So a spring type non-return with only a very light spring, kind of as you see in non-returns and mixing valves, or maybe a swing check valve in that ring main non-return, so that the pump's not going to not be able to open it and nothing happen, and a valve either side of the pump. So the last step that we want to do is check this velocity, that the velocity in our ring main return pipe is going to be under 1 metre a second, and we've got 0.7 or so meters per second of velocity, so we're good to go. Now, what I would generally do is go through and check that with my probable simultaneous demands applied to my supply pipes, that I put those flow rates in my supply pipes into the flow at the top, and just check down this velocity column to make sure that I hadn't exceeded those supply flow rates in my pipes. But we can see here that for our return pipe, we're good to go at 5 litres a minute. So let's have a look at UV sterilizers on those warm water systems. So we size it for the ring main return flow rate. Now, if you have a bigger pump, you're going to need a bigger sterilizer. So if you size the sterilizer and it was close to the ring main flow rate, and some genius decides to put a bigger pump in, you need to put a bigger UV sterilizer in potentially. The quicker the water, so the water is going through the UV sterilizer, it's getting bombarded with UV and it's killing the bugs. If you put the water through it faster, the water is not next to the UV for as long a time and it doesn't sterilize as well. So we don't want to go silly on the pump size, because then our UV sterilizer will also get really big. So we're looking for about a 40 millijoule per centimetre squared dose. That doesn't mean anything other than that's the column you want to look up in your UV suppliers catalogue. So small systems for your domestic houses, sort of with half-inch connections, are likely to have a non-amalgam bulb. Larger ones will have an amalgam bulb, and they're good to higher temperatures because the amalgam bulbs regulate the vapor pressure inside the lamps, and they aren't affected as the temperature gets higher. The smaller ones don't do that. So the dose is usually specified in smaller systems at 40 degrees. So what you need to do is, if you want to use a smaller system, which most of us do, you need to get off to your supplier and ask them, what's going to happen if I put 50-degree return water through your system? And hopefully they can tell you, as UV Guard told me for their units, take our specified flow rate and halve it. Now that's for the UV Guard units. If you're using a different unit, you need to talk to your supplier and see what they say. They may say you can't use it at all, or they may give you some other rule of thumb to work with, as UV Guard gave me. So if I look at my pump sizing example, and of course everybody wants to use different units. So 5 litres a minute, 300 litres an hour, 0.3 of a cubic metre an hour. If I bring up UV Guards, a couple of UV Guards models, we've got an S series and we've got an Armour series model. If I look at the small one that I really want to use, because it's sort of got the pipe fittings that are going to match my return pipe, I can see that at my 50-degree return temperature, or 55-degree, my 50-degree return temperature now, 45-degree return temperature, I'm not going to chin the bar, so I need a bigger unit. So I could go up to my S30 underneath, which has got plenty. They also have a nice, but then I'm up to bigger pipe fittings. In their sort of higher end range, they've got this one will do a little more than what I've got, so we can crack into it with the ARM1 model. Now you notice a bigger one at the bottom here that has an amalgam bowl. Its flow rate is not changing because it's good for 60 degrees. So on bigger buildings, you generally want to go with an amalgam one. On the small buildings, because we want small units and they're less expensive, we want to go with, we usually go with a non-amalgam lamp, but we need to make an allowance by consulting the manufacturer for the fact that we're not going to get the full dose at that higher temperature. So if we have a look at a typical UV sterilizer, it's a long sort of stainless steel tube looking thing hanging on the wall. As I said before, we need to leave enough room out the end to get the lamp out. Now the lamp sits inside a sleeve, and the sleeve is what's sealing the water away from the lamp. And the sleeve is made of quartz and it's transparent. And you need to get the sleeve out and check that the sleeve hasn't gone horribly opaque, or that it hasn't picked up a whole lot of muck and need cleaning. So the bulbs are replaced annually. You can just replace the bulb, but what you're really supposed to do is get this quartz sleeve out and have a look at it and give it a clean if it needs it. Now, the good news is that's plumbing work because you're into the potable water. So you might want to suggest to your clients that, after the first year, you'll come back and have a bit of a look at that quartz sleeve. Make sure you've sold the customer a few sleeves and a few lamps as part of the whole job, so they've got them there waiting for you to change. And if you take the quartz sleeve out and it's clean as a whistle, well, then you only need to change the bulb next time, and you can go a few years without having another look at the sleeve, which means you don't have to sort of depressurize and drain the system. But the sleeve's often forgotten about. And if that becomes opaque, obviously the UV is not going to get into the water and it's not going to work properly. So then we've got the lamp. We're going to replace that annually. They're pretty delicate, but as I said, add to your quote a few of these lamps and then maybe try and talk the customer into letting you service that regularly for them. There's generally a controller. It hangs on the wall. It beeps furiously if it detects that the lamp has failed. You can hook it up to the customer's burglar alarm system if they really want to get carried away. And it usually has a countdown timer on it showing how many days to go, so that the customer knows that it's time to get you around to sort out the lamp and give the quartz sleeve a bit of a clean. Expansion vessels. They're a pain in the neck, to be honest. You absolutely need them on a heating system, because on a heating system, we don't want to be discharging water out of an expansion valve, because it's going to take with us the treatment stuff that's stopping the system from corroding. Some people like them. Some territorial authorities encourage them on larger buildings. I'm not a great fan of them. The reason being that the bladder in them, they've got an expanding bladder in them, can fail over time. The customer doesn't know, and then the TPR valve on the cylinder's going off. So, yep, you can use them. Some people like them if they want to. That's all good. If you're going to install one, again, a Pete's plug, so you can have a bit of a look at the pressure. You want to be able to isolate this from the water pressure and vent it to air. So what you do is you set the system going usually with a fixture open. Eat your lunch while you see what sort of pressure you're typically getting. Isolate this, do this with this isolated from the plumbing system. Open this to air, and then what you want to do is pump this up to the pressure that you've basically observed in the system. If it's a bigger one on a bigger building, if you've had a lippy apprentice, you can give them a bike pump in a 300-litre tank, and that'll shut them up for a while. Once you've got this pressurized to the system pressure, you can open the system, bleed all the air out of it, and then once you bleed all the air out, shut it off, and away it goes. Once you've done that, you want to heat the system fully from cold to hot, and check that you haven't got anything coming out the expansion control valve or anything coming out the TPR valve, and that the pressure of the system's about right. Pressure vessel sizing. There's an appendix way down the back of 3500.4 that you might have never come across, Appendix P, that's got a method for doing that. We're running out of time a little bit, so I'm not going to go into detail, but again, we've got a spreadsheet. It's on the second page of the spreadsheet for the pipe sizing, and we'll make that available to you after the webinar. You can use it if you want. So we want to minimize the running cost. As I said earlier, the heat loss from the ring main is a fixed cost. So the first thing we want to do to fix that up is insulate the ring main. And then the second thing we want to do is insulate the ring main better. So we recommend 25mm thickness. More is better. This is what good looks like. This is a commercial job. You can see they've taken the valve handles off. They've insulated the valves. They've put the valve handles back on. This little glowing thing up here is the sight glass for the UV sterilizer. So they have insulated the UV sterilizer and created a little port there for the, so you can still see the lamp. They haven't, this end is where the bulb comes out, and you can see there's room to get that bulb out. But this is first class job. This is reducing that fixed running cost for their customer. In cold places, obviously try to run the ring main inside the building envelope. In Queenstown, don't run it through an uninsulated attic for miles. Second thing you can do to minimize the running costs is control the pump. So turn off the ring main pump with an external timer. We had a customer that reduced their LPG use by 40% by simply adding this onto an existing pump on a little rapid demand duo system that they had on their big house. So a timer, turn it off overnight, turn it off when you're away for the day. Consider a ring main pump with a temperature sensor. I'll talk about that in a second. So what we can do with that is we can shift our pump down to just past the furthest offtake point. If it's got a temperature sensor, the water will flow around. The pump will know when it's up to temperature, and it will turn off, and it won't fully heat the ring main return. When the water cools down a little bit, the internal temperature sensor on the pump notes that, and it turns the pump on again for a short period till the temperature rises up again. So this is one range of pumps that will help you out in this respect. The other major brands will have similar things. Again, I'm not getting anything from Grundfos for this. The prices there are sort of something of a trade price, excluding GST, that you might see something like that from your merchant, just so you can see the relative prices of what it's going to cost you to do this. So the one on the left, just a simple pump, runs 24 hours a day, but you can put an external timer on that and turn it off overnight. The next one's got an internal temperature sensor on it. It will, as I explained in the previous slide, see the temperature rising up in the ring main, and it'll turn off. It's got a cool algorithm in it that works out when to turn off and turn on again. The third one has got a little timer on it. It's got a little clockwork timer, a bit like an old-fashioned timer, but it's a digital one. So your customer can really simply set the time of day in order to, so it's got a temperature control and it's got a timer. So that'll really start getting your costs down. The last one here is auto adapt, which is sort of the top of the range for them. It has an external temperature sensor and an internal temperature sensor. What the external temperature sensor does is every time you turn a tap on, it notes the water temperature rising inside the pipe. And so it will learn the water use pattern. So it will only turn on for when it's expecting you to be using hot water. And it's got some tricky things that it does when you go on holiday and come back from holiday. You can see over here, the red thing is a temperature sensor. This little black band is a zip tie, and you tie it to the pipe, put a bit of insulation, and away you go. So the top of the range for them is the auto adapt. So there's lots of tricky things you can do with the pumps for, a sum of money, but not a huge sum of money to reduce your operating costs. So we've got lots of different water heaters. These will all be in the book. I'll cover a couple of them off because we're running out of time. Electric storage tank, you can just run round the ring main, back in the cold, job done. And these are the pictures that'll be in the book that show you how to do different ways. Heat pump water heater, different story. Heat pumps, inefficient, heating warm water to hot, and turning it on and off, just keeping the ring main hot, will wear the heat pump out really quickly. So what we do is we have a ring main reheating cylinder. We get a small electric cylinder. We run the heat pump feed into it. We run that around the house, and we run the return back. And the element in this cylinder is making up the heat loss of the ring main. So it reduces the wear on our heat pump, and it makes it work a lot more efficiently. And obviously the element in this needs to be big enough to overcome the heat loss that's been lost out of the ring main. But if you do the installation as you saw before, that'll be no trouble at all. And then we've got a couple of sketches in the book how to do that for a high temperature and a low temperature ring main. Rinnai Infinity, same but for a different reason. The burner can't go low enough to keep the ring main hot, and the water heater will go on, off, on, off, on, off its whole life, and it won't last very long, and it'll give lots of problems. So for Rinnai Infinity, again, we want the small underbench cylinder. This particular one that we do is an indoor-outdoor one. You can put this one outside. If you put it outside, you need to run the wire and a bit of conduit, or we'll get it hardwired. But that's a small 30 litre that you can bung outside. Again, we have drawings for single infinities, multiple infinities, high and low temperature ring mains. One tricky thing I'll point out quickly here is we can create a balanced pressure system by having, so you'll notice that normally we'd have the pressure reducing valve down here. We've got one on the cold and we've got one on the hot after the infinity. So the infinity has a reasonable pressure loss through it. So by having this arrangement on a high-end house, we can create a more equal pressure system, and it will just give a better outcome in high-end houses where you've got discerning customers. So it's something that you can consider. And that's the other one. So Rinnai Infinity NB56 is special. It can run the ring main. If we're sizing the pump, we need to allow for the pressure loss through the Infinity. Don't plumb it up like this, because as you all know, the hot and cold are actually the other way around. The Infinity powers the pump. When it sees hot water arrive back at the Infinity, it turns itself off. And we've got a whole document on our website about how this works, and there's a whole lot more in the book that you can have a look at. But we need 6 litres a minute, or the pump or the unit won't fire. So you might end up with some bit of 20 mil return pipe at times in order to keep your flow velocities within those required limits. And when you're sizing that pump, you need to add an extra 20 kPa for the pressure loss through that that unit, and the pump is driven from the NB. So again, we've got lots of drawings on how to do that. Rinnai Demand Rapid, so fast recovery gas, we bring that back into a higher port on the cylinder. If you're losing a lot of heat around the ring main, the tank will get cooled down quite quickly in off-peak periods by the ring main, and the boiler will turn on and off a lot. So the way to fix that is to put our favourite little ring main reheating cylinder in, set this to 60 or 65 degrees. It'll just top up that temperature of the ring main as it comes back, and the Infinity won't be wearing out, turning on and off really quickly. Some cases, it's not required. Other jobs, we've got relatively small tanks and relatively high ring main losses, and these can be a real benefit both for running costs, obviously reducing emissions, and also you're not wearing out your expensive boiler. That's it. I got there. Over to you, Alice, I think.
Thank you, Grant. Thank you very much for the very informative presentation. Now, before we jump into Q&A, I've dropped 2 links in the chat. The first is a quick survey about today's webinar. It will only take 2 minutes to fill it out. We're especially keen to hear what topics you'd like Rinnai to cover in future sessions. And the second link is for our next exciting webinar on the 16th of September, the future of LPG, a viable alternative today and tomorrow. We'll be joined by Jeffrey Clark, CEO of Gas NZ, and Chris Dolman, Head of Marketing for Linde South Pacific, which is VOC and L Gas, who'll be sharing some great insights. Now, the QR code is linked to the spreadsheet that was used in the presentation. If you're not a QR code person, don't worry, we'll email you the link and video of the recording in the next 2 days. Now it's Q&A time. First one, is there anything you have to consider for mixed temperature returns?
Mixed temperature returns.
Yes.
Not entirely clear understanding of the question.
I think that's what, unless, I think, let's see, Jacob said, is there anything you have to consider for mixed temp returns?
Okay. Again, I think I've covered everything in those drawings, and those drawings will be available in the book, which isn't too far away. Or you can have a look at them briefly on this webinar recording, or if you email info@rinnai.co.nz, we'll send you a drawing. And I really don't understand what you mean. So if you want to fire your question with a bit more detail into that, I'll be very happy to answer it.
Yes, that sounds like a good idea. And also, can I have a rain main system for a larger house with 2 hot water heat pumps together?
Yes, absolutely. You can do that. And we've done quite a few of those. The one thing okay, so as you go up in pipe size, you may need to go to a larger reheating cylinder. So we have so the one you saw obviously has the little one, 30 litres, has 20 mil connections. If you go to a larger pipe size, you might want to go to a cylinder with bigger connections. And we do a 57 litre commercial cylinder that's very reasonably priced. It has 3 elements in it for commercial use, but you only need to wire 1 element in, and that has 32 mil fitting. So you can push that down to 25 or use it at 32 mil. The second thing, if you're doing a bigger job with 2 heat pumps, is you need to be mindful of how close the heat pumps are together. You can't put them absolutely 20 mils apart. They need a little bit of distance between them because we need to draw air into the heat pumps from the surrounding air and expel it. And if we can't get enough air in, the heat pumps won't work as efficiently, and they may come up with an error if you've restricted the airflow into them too much. So they're just things to bear in mind if you're trying to do multiple heat pumps.
Excellent. This is from Brendan. Would it be possible for you to send a copy of your return pump sizing software through to assist our engineers sizing pumps?
Yep, so absolutely. If you scan that QR code, that's how you'll get that spreadsheet. You can download it and play with it. It's just taking the Kembla NZS 3501 copper spec sheet and putting it in a spreadsheet. Now, bear in mind, it is for the 3501 copper. So you want to do yourself something similar if you're commonly using other materials. But yep, scan that QR code and it's all yours.
Well, thank you.
Sorry, having said that, when you get the book, and if you download those spreadsheets, if you find any errors in them, please let us know and we'll have a chat about them and fix them up.
Right. And Daniel, to answer your question, will there be a recording sent for tonight? Yes, there will be in the next 2 days. Johnny, don't want to blow colder air from one heat pump to another heat pump.
Yeah, exactly. So you don't want the 2 heat pumps too close together. The Rinnai Hydra Heat, it draws its air from the sides and expels it vertically upwards. One of the reasons it does that is to minimize the noise, but it also has the benefit of you're not firing. If I can find a picture of it, maybe I didn't put a picture of it in. Yeah, so it draws the air in the sides and out the top, so it's less susceptible to you're not firing the cold air from one heat pump into the air intake of the other one. It's coming out the top, but you still don't want these too close together because we've got a reasonable volume of air we want to get in that vent, and we want to, there is a distance in the manual for the Hydra Heat that shows how far apart to put them to make sure you're not going to starve them of air.
And from Jacob, what are good balancing valves to use?
So again, if you have a look in the book, or you have a look on, again, I'm not on Waterways Pay. If you have a look on the Waterways site, they have a reasonably priced thermal balancing valve. And they also have a flow valve. For bigger buildings, there's a thing called a starred valve, which again, we explain how that works in the book. But for smaller jobs, you'll generally use a thermal balancing valve. There's a whole section of this in the book. You'll generally use a thermal balancing valve, and Kalifi do a nice little small one that Waterwell sell. I think it's a 116, but don't hold me to that. If you have a look on their website, you'll find it. Again, make sure you got the potable water one, not the space heating one.
And Grant, everyone's very keen on getting hold of the book. So when will the Rinnai book be available again? And
so it will be out before the end of next week. So we're just doing the final editing on it. We've had permission from people to use the pictures, and bearing in mind some of those people are competitors of ours in other areas. So we're just going to do a final edit, get out the last, dot the last I, cross the last T, and we'll send it. If you're registered for this link, we'll send it to you, so keep an eye out for it. It'll be before the end of next week, hopefully earlier.
And final question is actually from me. Who installed the insulation in that plant room?
Right, so Grant's favourite picture. So the commercial plumbers did that job. They contracted out that insulation to some refrigeration guys that normally work with heat pumps. Obviously, the refrigeration guys, if you don't properly and fully insulate a chilled water line, condensation will drip off it onto ceiling tiles and things and damage the building. So they are very, very pedantic about how they go about it, because they're used to doing chilled water lines. So sadly, that one wasn't a plumber. If you're a plumber and you've done a job like that, or you do a job like that, if you send me a picture, I'd love to put it in my slides rather than one that was done by the refrigeration guys. But they're potable hot water lines, but the installation was subcontracted out to a refrigeration company that was working on the same site, and you can kind of see why. They do a really good job. They do it really quickly.
Sounds like a great challenge, Grant. Now, and I think that's the end of the Q&A. So thank you everyone for joining us tonight. We hope you found the session useful, and we'd appreciate it if you could please take a moment to complete the short survey. Take care and enjoy the rest of your evening. Thank you again. See you next time. Mā te wā.